Up next we have Joanna Wu, again on the cosmic web and blue-centered galaxies in relation to it.
Hello. Okay. Thank you so much for having me here. So, blue-centered galaxies and the cosmic web. So that's what I'd like to talk about today. The motivation is that galaxies seem to be a two-parameter family. Okay, we have stellar mass and the radius of the galaxy. So we can, I plotted here, I've just made a really quick plot from the phone that you all can make, basically showing the quenched galaxies in red and the star-forming galaxies in blue, and you can see that the star-forming galaxies at the same mass tend to be larger than quenched galaxies. We've also done the same thing for this quantity here, which is sigma 1. This is the density of stars within the inner kiloparsec. It's a quantity that I have been interested in for many years, and several of my colleagues as well. But basically you see the same thing, because density, this central density, for star-forming galaxies that have an exponential profile, they are related to the radius. So what you can see here is that star-forming galaxies are lower density and larger than quenched galaxies. Now, there is a big range in size and density, core density, if you compare quenched to star-forming, but even within the star-forming population, which is what I'm going to be focusing on today, there is still quite a range. Now, right, for star-forming galaxies, sigma 1 is related to radius it's just m over r. You can take a look at the measurements here and check it all. Okay, so if you take these two planes, these two plots, and you color code by the measured SFR gradient in galaxies, this is what you get. So in 2019, Sarah Ellison and I published this plot here with sigma 1, the core density, versus m star for just star-forming galaxies and just isolated galaxies. We're not looking at satellites today at all, okay? Just star-forming galaxies. And the color code here is the SFR gradient, where blue means blue-centered and red means red-centered. So what you're supposed to see is that the blue-centered galaxies tend to be dense for their, stellar mass, and they tend to be small for their stellar mass. So they have small size and they have dense cores. Okay, I'm showing them both, but I'm showing both types of plots, but sigma 1 is basically the same as RE for star-forming galaxies only. All right, so star-forming isolated galaxies they're small and dense, and if they're small and dense, they tend to be blue-centered. So see also Aldo and Shauhan's talk from earlier this week. All right, so one of the questions we want to know is why? Why do galaxies have such a range of sizes, a range of densities, and why are they blue-centered? Why is there this correlation between blue-centeredness and galaxy size? So we wanted to find that out. This is observations. This is manga. So we wanted to check why, and one of the best ways to do it is to look in simulations. So we looked in simulations to see if we see the same thing. So this is TNG 100 at redshift 0, isolated galaxies star-forming as well. And we see the same thing here. It's the same plots, color-coded by SSFR gradient, and we can see that that blue-centered, whoops, I'm not used to this thing. Okay, blue-centered galaxies, that's blue-centered is blue. So blue-centered galaxies are dense, and they are also small. So we see the same thing in TNG 100. So this is perfect because we can track evolution in TNG 100. We can find out why galaxies are the way they are. Okay? So we checked a lot of things for why they might be blue-centered. We checked, Tumri Q instability. We checked a whole bunch of things, and what we had discovered was that it's related to the angular momentum of the accreting gas. So this is how we define the angular momentum of the accreting gas. So we have here streams coming in, and if they cross RV over 2, we calculate their mR cross V, and then we divide by m, so we get the specific angular momentum of the accreting gas. And we do this for the accreting gas, so that's all particles crossing half RV here. And we also do this for the disk gas to see what happens to the angular momentum as the gas is coming in. Okay, so we measured this quantity and we plotted against the two axes that we're used to, R versus M star and core density versus M star. And now the color code is that quantity, the specific angular momentum of the accreting gas. And what you find is that where the galaxies were blue-centered, they're accreting gas at low angular momentum. Same here in the sizes. Small galaxies, where they were blue-centered, they are accreting gas with low angular momentum. And that makes sense, right? Because low angular momentum means that the gas will fall into the center of the galaxy, and high angular momentum means the gas is falling on the outskirts of the galaxy. Okay, but there's more of a story to this. Oh yes, okay, so we actually showed explicitly the evolution of galaxies in this plane of the core density versus M star, and we tracked what actually determines how steeply the galaxy evolves, and it was the angular momentum. So what we found, this is the cartoon version of it. You can get the details, the actual technical details in Walters et al. 2022, but what we had found was that steeper evolution in this plot means that the galaxy is accreting gas with low angular momentum while star forming, and if you are evolving in a shallow way in this diagram, meaning that you grow your M star more than your sigma 2, more than your density, then you are accreting gas at high angular momentum accretion. And we also found that when they quench, the ones that accreted with low angular momentum quench quickly, and the ones that accreted with high angular momentum quench slowly. And we discovered this through the use of the age gradient. Basically, the ones that are quenching slowly, if they're quenching inside out, if they're inside out, then you quench the inside first, and it takes a long time to start quenching the outside. So their age gradients are such that you're going to have a young outside and old centers. And so that's a little cartoon of the age gradient here. And if you're quenching quickly, and you're quenching inside out, then your outsides will quench just as quick as the inside, and you have a more of a flatter age gradient. So we did find in TNG that the age gradient correlates with quenching timescale. And we had found it works out that the more massive galaxies quench slowly. That was a surprising result from this particular study, that the more massive galaxies quench slowly, even if they might start quenching earlier. They take longer to quench than the less massive galaxies. And we speculated that was because, well, they have deeper potential wells. It's harder to get the gas out completely from a deeper potential well. But please do see details here in Walters et al. Because I'm going to spend the rest of my talk just on star-forming galaxies and how they evolve. All right, so why is it then, if angular momentum of the accreting gas is related to how galaxies grow while they're star-forming and how they quench, why is it that some galaxies accrete gas with lower angular momentum? What causes them to be blue-centered? Why do they? Well, so that it's the angular momentum of the accreting gas that might be related to their blue-centeredness, but why do some accrete with low angular momentum and some others not? So the idea that we wanted to test was that the position in the cosmic web determines the angular momentum of the accreting gas. Okay, so if you are in a thinner filament, so the idea is, so we did hear today lots about filaments and the multi-scale structure of filaments from just now from Charlotte. So if we're in a really thick filament and we have your galaxies could be distributed anywhere in the filament, so farther from the center or closer in. So you are more likely to have gas fall in with higher angular momentum. You might be in the vortex region, and from Nir and Sharon's talk about these really thick filaments here. So you might get a little bit more accretion with higher angular momentum. However, if you're in one of these really thin gossamer filaments, then you're more likely to be right near the center of it, and you're more likely to have gas fall in with lower angular momentum. So this was the idea that we wanted to test in the simulations, in TNG 100 in particular, at redshift 0. However, keep in mind that the scale of the accreting gas coming in the halo is much, much larger than the scale of the galaxy. So we still need to deal with angular momentum loss to get the gas all the way into the galaxy. And the angular momentum loss is determined by the orientation of the galaxy's spin relative to the accreting gas, as we learned in Danovich et al. In 2015. So we do have to keep that in mind as well. All right, so we started testing this idea where we plotted here the specific angular momentum of the accreting gas versus the density of the dark matter around the galaxy. And so the idea was that these big thick filaments are going to have higher density. So these are the thick filaments and these are the thin filaments. And we plotted this in different mass bins for the galaxies. And we do find indeed that thicker filaments accrete gas with higher specific angular momentum at all masses. So this is good, but we still need to test whether or not, the thickness of a filament or the thinness of a filament is related to the density of the dark matter. Is it related to the density of the filament? We needed to test that explicitly, so we went ahead and did that using the filament catalog that Farhan here in the audience has run using the slime mold description of the cosmic web. So this is, I'm sure we're going to hear a lot more from Farhan later today for more of the details of how this works. But basically, the traditional way of running disperse, which is the most common code for measuring the cosmic web, is to do this Delaunay tessellation of the dark matter distribution, where the tetrahedrons here are the positions, where the tetrahedrons where the vertices are the positions of the galaxy. So the novel method that Farhan and his collaborators applied to the cosmic web was use this algorithm based on how slime mold grows, where you can use the algorithm to produce a map of the probability density function of the agents that move towards food. So if you have galaxies being the food sources and you have agents moving towards food sources, then you end up with a map very similar to this map right here. And you can see that the slime mold prescription replicates the dark matter distribution a lot more closely than the Delaunay tessellation algorithm. Okay? So we'll hear more details from Farhan, I'm sure. And Farhan has also shown how filament properties correlate with galaxy properties. And what we did here was we took the filament catalog that Farhan kindly gave us, and we measured the density profiles for a bunch of filaments. So this is an example filament, and here is on the y-axis the density of the gas in that filament versus distance from the center of the filament. So you see this nice declining profile here. The purple is the smooth line to the red line is the actual data. The purple is smooth. And we define the filament density to be the density at the center of the filament. And we define the thickness of the filament to be the point where the density falls to about twice the box density, twice the box density of gas, NTNG 100. Okay, so that's what we define as the density and the thickness. And then we plotted them against each other. And here we have the filament thickness, as I defined it, versus the filament density. I just realized I reversed the, okay, it's fine. So filament thickness versus filament density, and the contours here are the number density of filaments in the plot. So this is a filament plot, not a galaxy plot. And you can see that they're quite correlated. So the denser your filament, the thicker your filament is by our definition. Okay, so that makes a lot of sense. Thickness is correlated with density. This is color-coded by the length of the filament as well, so you can see that shorter ones tend to be in denser filaments as well. And here is a plot of filament density versus the distance from the node. Almost all the filaments have a node at least on one end, and then if you measure the segments, the thickness of the segments along your filament, you actually do find that the density correlates with distance from the node. So as you go farther away from the node, you get less and less dense. So these are some properties of the filaments that we've learned about the filaments. So we're more interested in galaxies, so let's look at how the galaxy properties correlate with these filament properties. Okay, So the first thing, now this is a plot of the galaxies, not the filaments, okay? So the contours represent the number density of galaxies in the plot, and now we have reversed it, sorry about this, but we've reversed it, put density on the y-axis and thickness on the x-axis. But that's the density of the filament that the galaxy is nearest to. And this is the thickness of the filament that the galaxy is nearest to, okay? So this is a galaxy plot. So again, there's, you know, a correlation between filament density and filament thickness. And now we've color-coded by the specific angular momentum of the accreting gas. So accreting at half RVR here. And you can see that galaxies in thicker and denser filaments accrete gas with higher specific angular momentum. So this is exactly what we were expecting. Thicker filaments accrete, galaxies in thicker filaments accrete with higher specific angular momentum. This is now the same plot, but color-coded by the specific angular momentum of gas in the disk itself. So we can see the numbers on the color scale are lower, so gas has lost angular momentum overall, but here we've lost, in this region, we've lost a bit more. So what's going on here? So the specific angular momentum of the gas in the disk also correlates with filament density, except in this region. And what's going on in this region? Well, we remember Danovich et al., where if your orientation of your galaxy is misaligned with your accreting gas, you will tend to lose more angular momentum that way. So here is the same plot with the same axes, but now color-coded by the alignment between the specific angular momentum of the disk and the accreting gas. So that alignment is such that the red in the plot means aligned, and blue means misaligned. And here we see that this area of the plot is where the galaxies are more misaligned. Okay, so the specific angular momentum of the gas in the disk correlates with the filament density, except where the specific angular momentum of the disk and the accreting gas are misaligned. Okay, so here we have, so this is, for example, the angular momentum of the disk, and this is the angular momentum of the accreting gas. This little cartoon illustrating this. All of this, by the way, was done by my student Marcus Cowan, who is an undergraduate student and is looking for a graduate position. All right. So we wanted to look at this a little bit closer. So what we have here now is the alignment on the y-axis between the disk and the accreting gas. So red, or actually no, sorry, top is aligned, bottom is misaligned, and now plotted against filament density. And now color-coded by the specific angular momentum of the gas in the disk, but it's very similar as the accreting gas as well. So what we see here is that the gas specific angular momentum depends on both the filament density and the alignment of the galaxy to the accreting gas, such that you have lower specific angular momentum for misaligned galaxies. Does that make sense? Because you are more likely to lose more angular momentum if you are misaligned. But it's not just the alignment that matters, it's also the filament density. We get lower specific angular momentum in thinner filaments, thinner or less dense filaments. I'm kind of putting density and thinness as being the same thing because they're correlated with some scatter, but they're correlated, okay? So there's more to this story, because the mass of the galaxy also depends on the density of the filament. So we have more massive galaxies living in denser filaments. And remember that I discussed at the very beginning that galaxies are a two-parameter family. So in order to understand why galaxies are larger or smaller, we need to take away the mass effect. So we're going to take away the mass effect. So if you remember this plot I showed earlier, size versus mass, sigma 2 versus mass, you can see that we're color coding by the specific angular momentum. We can see that there is a mass dependence here. There is a mass dependence as well as a size and density dependence. So let's take them out. We're going to take out the dependence, and we're going to subtract the average dependence on mass. And now we're color coding by delta, that's a relative specific angular momentum relative to its mass in. And so now we've basically taken out all of the, you can see that this is taken out all the mass dependence. Okay, so when we take out all the mass dependence, what do we get for these plots now? We have the alignment versus density. and we have now color-coded by the relative angular momentum, and we still get the same behavior. Basically, we get that relatively lower specific angular momentum when you're misaligned and when you're in thinner filaments. And same here. Okay, and we also, this is color-coded by the relative SSFR gradient, so we get relatively bluer centers if we are misaligned, accreting at lower angular momentum and in thinner filaments. So all of this is starting to make a coherent picture of what's going on with these galaxies. Okay, so lower relative specific angular momentum and bluer centers for misaligned galaxies, as well as in thinner filaments. And lastly, we have the alignment versus density, color-coded by the size of the galaxy specifically. Okay, so this is the relative size. We've already taken out the mass dependent. And this is the relative core density, taking out the mass dependent. And what we get is exactly the same thing what we expect. Smaller sizes if the accretion is misaligned and if it were in thinner filaments. And we also have denser cores if we are relatively denser cores, if we are misaligned and if we are in thinner filaments. So in summary, small and dense galaxies are bluer centered and accrete gas with lower specific angular momentum. And in terms of the filament properties, denser filaments are thicker and thinner filaments are less dense. And also the galaxy properties correlate with both filament density and the alignment of the accreting gas. Okay, so the misalignment of accretion to galaxy, the accretion to galaxy misalignment results in lower. We'll do it the opposite way. So we have red-centered, high specific angular momentum accretion, and larger sizes and diffuse cores if we are aligned with your accretion and if we were in thicker filaments. And we have blue-centered, lower specific angular momentum accretion, smaller size and denser cores if we are misaligned or in thinner filaments. Thank you very much.
All right, any questions? I saw this one right here first.
Thanks, Joanna, for the enlightening talk. I really feel this story is compelling, but also, and at the same time, sort of hand waving, because are you essentially equating the impact parameter of the gas accreting onto the galaxy to the thickness of the filament? But we know this is oversimplified for several reasons. One, the gas stream is always at the spine of a cosmic filament, and two, it's not directly onto the galaxy, it's through the halo. So there is maybe a CGM, then cooling flow. So how do you reconcile this? Is it possible that the thickness or the density of the filament just provide a large-scale environment for the halos?
Yes, very good question. Exactly. So we're accreting onto the halo. We're not accreting onto the galaxy. There is angular momentum loss that has to happen before the gas gets onto the galaxy. But what we've shown here is that there is a correlation with the alignment of the galaxy to the angular momentum of the accreting gas. So they will lose angular momentum, but if you already start with lower angular momentum, then you'll end up with lower angular momentum overall. So that's kind of the idea.
Why are you misaligned? In other words, should we be thinking about the enduring persistence of the angular momentum over time?
That's a very good question. So it turns out that the vast majority of galaxies here are more or less aligned. So if you are misaligned, then you end up getting these blue-centered galaxies, and you get more of this effect. But the majority of them are aligned. As you can see in the black contours here show that they're more aligned.
Okay.
Good question.
Remember to say your name before you ask your question, if you would.
Roberto Agnolino, Cambridge, UK, Cambridge. And the finding that small-mass galaxies quench more slowly, while low-mass galaxies quench more quickly, must be a very local phenomenon, because the vast majority of passive galaxies show a correlation with the alpha over Rhino enhancement, which is a tracer of how fast quenching happened, and means that massive galaxies quench much quicker, much faster than low-mass galaxies, and this is also traced by the star formation history. So must, so this finding must be something that is associated with the local universe, not with the bulk of the cosmic books.
So we did check, so for that particular paper, we did check the evolution of these galaxies throughout cosmic time. And it seems like the massive galaxies still have, like, you know, a little bit of star formation on the outskirts for a long time, keeping them in the Green Valley until for a long time. So it seems like if in the observations that is not detected, the outskirts too dim to be detected, that might be the reason why we're not detecting this this residual younger population in the outskirts. But what we have found, though, is that in manga galaxies, manga quenched galaxies, the age gradients are exactly what we expect. The more massive quenched galaxies have steeper age gradients, whereas the lower mass quenched galaxies have flatter age gradients, which is exactly what you would expect if the quenching is inside out and you have faster quenching making flatter gradients, slower quenching making steeper gradients.
All right, thank you, Joanna. Let's everyone thank her again.